Alright, hello Calc geniuses. So, sorry it's a little later than I anticipated. I'm trying to zoom in here just a little bit. So, this is the problem we started in class. And it is water is being pumped into a pool. This is the pool that we had in class. And this angle here, by the way, is supposed to be a right angle right here. And then the bottom of the pool is sloping upwards, so that should be a right angle. So water is being pumped into a pool at 5 cubic feet per second. When there is 2 feet of water in the deep end, how fast is the water rising? So there's our diagram right there. We notice that the pool is 15 feet in length, if you will, because I'm going to reserve the word height for the triangle that I have here, height, and the base is right there. And we know that the base at maximum is 20 feet, and the height at maximum is 10 feet. So the first thing we need to do is find a relationship, and as I said, these were going to be a little more difficult because the relationship isn't just handed to you like, 1/3 pi r squared h for a cone or something like that. So we need to find the volume of the water that's in the pool here. And so if you can imagine, as we're 2 feet here, I'm going to go across at 2 feet, or at least I'm going to try to go across. And so there's our little triangle of water right here, and it's a right triangle of water, and it goes all the way across to the other side of the pool here, so that we have this triangular figure right here, or wedge shape, as it were. And so there's our wedge right there. And so, as I've talked about many times, the volume of something that's fairly regular is the area of the base, which in this case the base is clearly a triangle, times the height. But in this case I'm going to call the height the length, which is going to be a steady 15, not going to change at all. So we need to create our volume expression here. So we have a volume equals, so since the base is a triangle, I'm going to write down, remember, it's the area of the base times the height. 1/2 base times height times, in this case, length. I'm doing the length there because I'm keeping height for the triangle. And we have 1/2. And we can see that the ratio of the base, which is here, to the height, which is here, is 1 to 2, because it's 10 to 20. So the base is half of the height. So I'm going to have 1/2 of the height, because base is half the height, times the height again, and times 15. So there is the beginning of our volume expression. So again, we got 1/2 base times height for the triangle times the length, and the base is 1/2 of the height, 10 to 20. Base is half the height. So we just kind of put this all together here with a 15 in front and the 1/2 times 1/2, so we have 15/4 h squared is the volume. So now we just do the derivative of that using implicit differentiation. I'm going to structure this a little bit better. So we have dv dt equals, bring down the 2 in front, so we have 30 over 4 times h times dh dt. And we know from the beginning of the problem that the volume is increasing at a rate of 5 cubic feet per second. 30 over 4 is the same as 15 over 2, or 7.5. The height that we are being asked, or we are told that the height is 2 feet when we are asked about the rate of change of height, so we're going to put in a 2 here. And dh dt we don't know yet, but it's pretty obvious what it's going to end up being. So then we got 5 equals 15 dh dt, or we divide both sides by 15 and we get dh dt equals 1/3 of a foot per second. And there you go. So let's move on to the next problem, which is somewhat similar. And again, I didn't structure my stuff here very well, but it's okay. So this is the trough problem. And I didn't quite draw it to scale, but you'll get the idea. So we have a trough here, which is a triangular trough. And so again, it has some similarities to the pool that we just did here, because the base is a triangle times the length. So water is poured in at a rate of 4 cubic feet per minute. How fast is the water rising when the height is 2 feet? So again, we have to do a little bit of constructing of our volume function here, because again, this is about volume and height. So the volume, again, is going to be so the area of the base. So again, we're talking about this little bit of water right here, which is triangular. So it's the area of the base times, in this case, the length. And again, we have a triangle. So it's 1/2 base times height, so that's the area of the base, times the length, which in this case is going to be 10 feet. And here again, we have that the base is 1/2 the height. So base is 1/2 the height, so again, we're going to put that right in here. So we're going to have 1/2 times 1/2 times the height times 10. So there is our the beginning of our function. So then we write 10/4 or 5/2 h squared is our volume. 5/2 h squared. So again, just do the derivative, easy enough. So we do dv dt equals, the 2 is going to come down in front and cancel off the 2, so we're going to have 5h dh dt. And we know the height is supposed to be 2 feet, so that's obviously going to be 10 dh dt. And the water is flowing in at 4. So we divide both sides by 10, and we get 0.4 feet per minute equals dh dt. Okay, and then we move on to a definitely more tricky problem. And I've done a little work ahead of time here. Actually, I've done most of the problem all the way through, because there was just too much trig and too much calculation to not do that. Okay, so here's the problem. So a balloon rises at 5 feet per second. An observer 150 feet away measures the angle of elevation. How fast is the angle of elevation changing at 10 seconds? So I already drew the diagram for us. So we got theta down here, and our observer is right over here. I guess I should have drawn a little observer right here. So there's my observer. And the observer is 150 feet away from this balloon that's rising up at 5 feet per second. And this is our y here, right? Because up and down is y, because we're going to need that in a moment. And 50 feet. Okay. So at 10 seconds, we're able to calculate that in 10 seconds, the balloon that's rising 5 feet per second gives us 50 feet right here. We're going to need that also in the problem. So, again, we start off with the diagram as we already did, and then we need a relationship. So, here we got theta here, and we got something, a variable, something that's changing, y, over here. Variable is changing, y over here. And in this case, the other quantity here in the triangle, the base of the triangle here, is not changing, 150 feet, not changing. So then we can set up our relationship that tangent of theta equals y over 150. So y over 150. And then we go ahead and take the derivative of that. So the derivative of tangent theta, of course, is secant theta d theta dt, remembering that, of course, theta is inside the function, so we got to do the derivative of that too, equals 1/150th dy dt. And the variable doesn't, it just kind of disappears, and we just have dy dt. And then we go on a little bit further here. So in order to actually do this problem here, so here we have the derivative, we actually need to know what theta is. So back up to the diagram here, we have theta here, we have 50 here, we have 150 here, so we know that the tangent of theta is 50 over 150, or tangent of theta is 1/3. So we want to know the angle whose tangent is 1/3. So inverse tan of 1/3 turns out to be 18.43 degrees. But we don't really want the tangent of that, we really want the secant of that. Or actually the secant squared of that, so the secant squared of 18.43 turns out to be 1.111. Now we can just plug everything into the derivative that we found. And so 1.111, which is secant squared of theta, times d theta dt, equals 1/150th, that's from there, times dy dt, which we know to be 5, because that's how fast the balloon is rising. And then just doing some little calculations here, turns out that d theta dt is 0.03 degrees per second. As you can imagine, the balloon is actually rising fairly slowly here at 5 feet per second. That's not a very fast rise at all, so that's why our angle isn't changing very quickly. Alright, on to our last problem. So I set it up here, and I was going to do the problem down below, but then I realized I should also have done all the calculations, so I did all the calculations. So a plane is 4 miles above ground, flying towards a point directly above an observer at 300 miles per hour. How fast is the angle of elevation changing when the angle of elevation is 30 degrees? So if you can imagine, you're standing there, at your house or whatever, and you see a plane flying towards you at 300 miles an hour, and it's 4 feet above the ground, and so you're watching it as it comes towards you, and as it comes towards you, you can imagine that you're looking more and more up, or more and more straight up as it gets closer and closer to being, directly overhead. So somewhere I actually have this problem done. Oh, here it is. And it's right here. So this was kind of my rough work to begin with, and then I realized, okay, I'll just leave it because it's not that rough. Alright, so here's our triangle, and so we have the observer over here looking up at the plane that's 4 miles in the air, and the plane is flying towards the observer at 300 miles per hour. So how fast is the observer tilting their head back as the plane flies across this way? So I chose to draw the triangle this way. I could have drawn the triangle up here instead, but I like the angle of elevation better expressed this way. So again, we have to find our relationship. So we got the diagram, now the relationship. So again, it's tangent, so it's we have the opposite and we have the adjacent. In this case, the opposite isn't changing, but the adjacent is. So there are some similarities to the previous problem. So we have tan theta equals 4 over x. Should have x right here. 4 over x. And so when we do the derivative, actually we rewrite this so that we can find the derivative. And one more thing. I know, or so we both know, we all know, that when we do the derivative of this, at some point we're going to need to find out the value of x. So I'm going to do that right here. So as it turns out, the angle is 30 degrees, which was given in the problem. So the tangent of 30 is 4 over x. So the tangent of 30 equals 4 over x. I'm using that information so that I can find the value of x, the distance from the observer to where the plane is, or at least a point directly under the plane as it's flying towards the observer at that moment. So, so we have the tangent of 30, which is 0.5774, equals 4 over x. Do a little quick switching and calculating. As it turns out, x is 6.928 miles away. So the observer is 6.928 miles away, which we can have right up here, 6.928 miles away. So now we go back down here, and we do the derivative of this function right here. Tangent theta equals 4 over x, or 4 times x to the negative 1. And we do that right down here. So we got the secant squared of theta times, bring down the negative 1 in front of the 4, so now we got negative 4x to the negative 2 dx dt. And then, again, we have to do something with the angle there. So we have secant squared of 30 degrees, which is the same as 1 over cosine of 30 degrees squared, which turns out to be 0.75. If I had done that with radicals, it would have come out just as easily. So as it turns out, we're actually almost done with the problem. So 0.75 was the secant squared of theta times d theta dt, which is what we're trying to find, equals negative 4 over x squared, and x was the distance from the observer to the point directly under the plane when the angle of elevation was 30 degrees. And then we do times dx dt. And this is going to be negative 300 because the plane is flying towards the observer and decreasing the distance between the observer and the plane. Or we could also think of it in terms of, as we're headed left on the x-axis, we're going in the negative direction, so negative 300. And then again, doing some calculations here, it turns out that d theta dt is 33.33 degrees per hour. And as the plane is fairly far away, we have the angle that is changing fairly slowly. As the plane gets closer and closer to being directly overhead, the angle of elevation will change more rapidly. So that's why this is not changing all that quickly. So 33.33 degrees per hour. So that's the instructional part. I'll post an assignment along with this video that's going up onto YouTube presently, and then I'll post that on Classroom. So I will see you tomorrow. Thanks. Bye.